We are currently experiencing minor security difficulties. We apologize for the inconvenience.
Even though we have a little security problem on our hands, we must prepare you for temporal displacement. That's time travel to you. Now, it's crucial that I spend a little time going over the basics of time travel. Perhaps this demonstration will suffice.
As I'm standing here on Earth, gravitational forces pull straight down on me. The surface creates a perpendicular normal force pushing up on me. My vertical forces are balanced or equal. Because nothing is happening to me horizontally, my horizontal forces are also equal. 0 equals 0. Some other forces that could act on me. Anytime I have a general push or pull, we would call that an applied force. If that force involves a rope or a string, we would call it a tension force. Right now, my feet are rubbing against the ground, creating a friction force. That friction force can either be kinetic or static. I'm not moving, so this is static friction.
The forces that act on an object define the object's motion. If the opposing forces are balanced, the object is moving with a constant velocity or it's stopped. Balanced forces create no acceleration. Here's an example of vertical balanced forces. When the forces opposing an object are unbalanced, the object is either speeding up or slowing down. When forces are unbalanced, one force pulls more than the opposite force. For example, this horizontal applied force is pulling more than this horizontal friction force. These unbalanced forces create acceleration.
Ready! Cut!
Let's analyze another one of Doc Brown's time travel experiments from 1955 to Hill Valley's Old West in order to understand the forces behind the motion of time travel. In this research footage, test subject Marty McFly speeds up from rest to a velocity of 88 miles per hour, or about 39 meters per second. As he travels through time, he briefly travels at a constant velocity of 88 miles per hour. When he sees the welcoming party, Marty slams on the brakes and slows to a stop. When Marty speeds up to 88 miles per hour, his vertical forces are balanced. Because he's speeding up horizontally, his horizontal forces are unbalanced. One of the opposing forces has to be bigger than the other due to this acceleration. Let's describe the forces acting on the DeLorean. The gravitational force, or F sub g, pulls straight down. The gravel parking lot creates a perpendicular normal force, or F sub n. The car is pushing forward, an applied force, or F sub a. And the wheels and gravel create friction, or F sub f. My horizontal forces are unbalanced. I'm applying more force forward than friction is pulling back. Some of these forces can be calculated. For example, if I know the mass of the DeLorean, according to Google, 1,230 kilograms, I can calculate the gravitational force by multiplying by 9.8. The gravitational force constant here on Earth. Since my vertical forces are balanced, I know that my normal force is also 12,054 newtons. The DeLorean is driving on gravel. The coefficient of friction is 0.6, or in other words, its mu is 0.6. This value multiplied by the normal force tells us how much friction is pulling back on the object. When I find a piece of information, I add it to my force diagram. The DeLorean's horizontal forces are unbalanced because it's speeding up. So in this case, the friction force is less than the applied force, so I can't calculate the applied force. I do know that it has to be bigger than 7,232.4 newtons. There's our force diagram describing the DeLorean as it speeds up driving forward. When Marty travels at a constant velocity of 88 miles per hour, his vertical and horizontal forces are balanced because he isn't accelerating in any direction. The opposing forces are equal. Let's analyze the forces acting on the DeLorean as it drives at a constant velocity. Gravity pulls straight down. The normal force is perpendicular to the road. As the DeLorean drives, an applied force is applied forward. friction pulls back as the tires rub against the gravel. Just like last time, we can calculate the gravitational force. Because we know that it's vertically balanced, gravitational force equals the normal force, we can also calculate our friction force. In this case, we're transitioning from gravel over to sand in the Old West. So the mu is lower, 0.3, times our normal force gives us a friction force of 3,616.2 newtons. Because our vertical and horizontal forces are both balanced, our friction force is equal to our applied force, and there's a force diagram describing the motion of the DeLorean as it travels at a constant velocity.
There's a lot you'll need to know if you're to successfully cross the space-time continuum. We'll have to hurry, though. With Biff still on the loose, anything could happen. Biff, how in blazes did you get in here?
Why don't you ask these bozos?
Doc, one of our time travel teams was conducting an experiment back in 1955.
He must have stowed away! We gotta get you back to 1955, or we could create a major paradox! I'm gonna take a little joyride.
No! Biff!
Love to stay and chat, Doc. I just ain't got the time. What am I saying? I got all the time I want!